All right, guys, I think we can start today's webinar. So good morning and thank you for joining us today for the final webinar of the DECICE project, an EU-funded initiative dedicated to advancing intelligent collaboration across the device edge cloud continuum. Over the next 90 minutes, we'll take you through the journey of DECICE from its strategic vision and technological breakthroughs to real-world applications that demonstrate its impact. You'll hear about our integrated AI scheduler, digital twin architecture, and virtual training environment, each designed to optimize performance, energy efficiency, and responsiveness in distributed computing systems. We'll also showcase 3 compelling use cases: intelligent intersections for road safety, accelerated MRI analysis, and emergency response support through edge intelligence. The session will conclude with a Q&A session offering space for dialogue and knowledge exchange. We're excited to share our results and insights with you, so let's get started. Before we continue with our today's agenda, I would like to highlight our housekeeping rules. Namely, our virtual event will be recorded and posted on the DECICE project website in order to ensure, according to the rules of open access scientific information, that all collected insights are openly accessible for all interested parties and can support further development activities in the field. Feel free to ask questions anytime in the chat option. We do our best to answer them during the event, and if you'd like to speak after each presentation, please raise your virtual hand. So that being said, I would like to pass the floor to the first presentation, which will be done by our coordinator, Mr. Felix Stein from the University of Göttingen, Germany. Felix, the floor is yours.
All right. Thank you so much, Alexander. Yeah, welcome, ladies and gentlemen, to our small webinar today. I would like to give you an overview of the DECICE framework and what we did. Alexander already mentioned it. DECICE stands for Device Edge Cloud Intelligent Collaboration Framework. And what we're doing is we are trying to build a framework that is able to schedule jobs on a heterogeneous compute continuum. Next slide, please. All right, I would like to give you a short overview, so to speak, right? So the agenda for this talk is like the overview and the key objectives. We had key exploitable results, challenges, as well as our way forward and how we want to continue the development of the DECICE framework. Yeah, starting with the overview and the key objectives itself, right? I already mentioned it. What we're doing is we are developing an open source cloud management framework that is capable of deploying jobs on a heterogeneous compute continuum, including HPC systems, cloud infrastructure, as well as edge computing. We're doing this with different machine learning and deep learning models. One of these is our sort of key AI feature, the AI scheduler for our dynamic job scheduling. It takes lots of parameters into consideration, right? Such as hardware requirements of the job that needs to be scheduled, as well as node information, such as the available hardware, and also interesting metrics like energy efficiency. We built this around APIs that allow for advanced control of all of these resources to users and admins alike. So they can easily interact with the framework itself, do some settings, setups, and then, of course, deploy the jobs. All of this is being sort of backed up and supported by a digital twin, which represents the entire system in memory to be able to like sort of asynchronously pull metrics and at the same time store them for easy and fast access. And then, of course, enriches the provided data with different machine learning models for carbon intensity, energy efficiency, etc., etc. And then, of course, the framework itself is secure. We have implemented few rules regarding role-based access control. We have a secure login system, etc., etc., and then we are following the GDPR rules of the European Union to secure or to ensure cybersecurity and compliance. Next slide, please, Alexander. Our key exploitable results sort of overlap with the overview and the objectives already talked about. So we have our DECICE framework, right, with the job scheduling on the compute continuum. We also provide a synthetic test environment where users can sort of tweak the AI scheduling by providing like different infrastructure, different job requirements, etc., etc. So we can simulate different infrastructure and sort of provide a broader testing as well as training approach. The AI scheduler itself, of course, another key exploitable result. This is sort of the key component of our work, which is doing the scheduling. It's written there, right, based on the status of the compute continuum, which is being reflected by the digital twin itself, right? It stores the data of the compute nodes, storage, as well as network resources. And then, of course, the data sets we created was not really easy to, well, this is a new approach and framework we developed. We couldn't rely on proper data sets, so we needed to come up with our own solution to provide like very sophisticated data sets to ensure a good and comprehensive training approach. Of course, these key exploitable results are not only for us, they're also for our target groups, which could be data centers, scientific communities, developers, startups, or even enterprise companies. Next slide, please, Alexander. Of course, the development of such a framework doesn't come without challenges, unfortunately. But over the course of, or the duration of this project, we mainly identified two problems we had, which is the provisioning of training and testing data for the AI scheduler, right? I already talked about it. We didn't really have a foundation to build upon, so we needed to come up with our own training and testing data sets, as well as not only synthetically creating them, but also finding a way of like setting the framework up, do some first very simple scheduling, and then of course take this data, clean it, process it, and then sort of refeed it into the scheduler itself. And then the second problem or the second challenge rather, we encountered is job scheduling on HPC clusters via our framework. While the compute continuum, HPC, cloud and edge, in and itself is already heterogeneous, there's also the issue that the HPC landscape is also very heterogeneous, right? So there's not really a one size fits all. And the framework itself should reflect this. The problem is that given solutions are either not production ready or they cover a very narrow use case. So we had to work on our own solution for that. The solutions for both of these problems, I already mentioned them, is that for the training dataset, for the AI scheduler, we had to collect and process and generate our own training data, either via synthetically created data or Prometheus or even our own data sets provided by Unibo. And then, of course, the HPC landscape, we focused on SLAM for this. SLAM provides a very comprehensive and sophisticated set of APIs, SLAM REST-D, which we can sort of easily access and deploy jobs to HPC while using these SLAM APIs. And of course, the outcome here is that we now have a sort of baseline data set for our training, for our AI models, as well as more control over HPC jobs. We can also pull accounting data for each users, and we provide a broader set of functionality as well as information compared to other open source alternatives here. Next slide, please, Alexander. Of course, the development of the framework itself sort of is an ongoing process, right? So here on this last slide, I just quickly want to talk about our way forward with the different systems and microservices we developed. First and foremost, the digital twin. Here, like when we provide new features to the AI scheduler itself, they need to be reflected inside the digital twin as well. And this is, of course, as I said, an ongoing process. And we continuously work on providing more training data, as well as more features for the AI scheduler itself, which are being reflected and stored inside the digital twin. Then the AI scheduler goes sort of hand in hand with the digital twin, right? We are focusing on extending the scheduling capabilities with new algorithms, strategies, and then also algorithms for like real-time optimization and predictive maintenance in this case. The workflow management system we implemented is also part of the DECICE framework itself. So users, we didn't want to push our users in one direction of how they want to upload or submit jobs. While we are using for HPC Slurm, for example, and then our orchestrator on cloud and edge as Kubernetes, there's a wide variety of sort of file formats that can be used in order to submit a job, or in this case, a workflow. And for this, we implemented a few workflow management parsing tools, right? So we are capable of providing users with the possibility of uploading jobs via a tool called SnakeMake, which is very broadly used in some parts of the scientific community. We also allow Argo, which is another workflow management tool, which can deploy a series of jobs via Kubernetes. We also provide the possibility of submitting SBatch files for HPC and Slurm in this case, as well as plain good old YAML files for the orchestrator. And then last but not least, the platform, the DECICE framework itself. As I said, currently we're running on Kubernetes. It's the de facto gold standard, if you will, right? But there are other platforms out there like Nomad or Docker Swarm, for example. And we also want to make our platform sort of agnostic, if you will, to support like different orchestration tools to deploy jobs. Yeah. Next slide, please, Alexander. That's it already from my side.
Great.
Yeah.
Great. Thank you very much for the really nice presentation, Felix. I would
You're
suggest
welcome.
that we keep our questions for the last slot, which is dedicated to the Q&A session, and move on with the next presentation, which will be done by Mr. Mirash Aydan, again from the University of Göttingen. Mirash, please feel free to take over.
Yeah, thank you, Alexander. Felix already mentioned a couple of things regarding DECICE, so I will talk about generally our solutions and innovations in the DECICE project. Next slide, please. Yeah, we majorly have 4 components as a solution in DECICE framework. Of course, we have sophisticated backend, etc. But I would like to focus on these 4 things. First of all, virtual training environment, and then digital twin, AI scheduler, and lastly, SLARM integration. Next slide, please. Yeah, virtual training environment is a synthetic test suite that we can replicate some system scenarios or what-if scenarios for our AI scheduler. We can basically evaluate different things, and also we can train our AI scheduler itself. And it also integrates with digital twin for data injection in our environment. So basically, you can bring your own data, your scenarios, and then you can inject this data to digital twin. And maybe if you want, you can filter your data. You can inject failures and faults for your system and application, etc. So virtual training environment is capable of doing that. And also, as I mentioned, it enables AI scheduler training in a controlled environment and also non-production environment. Next, please. Yeah, the advantages of virtual training environment. Of course, we are training the scheduler faster than real time because we don't have to wait for the real production data. We can easily replicate what-if scenarios for the system. And also, we can create an early pre-trained model before the production deployment. And lastly, it also improves the scheduler. We can use real-time production data after training the model. When we attach our AI scheduler to the real-time data, it will improve itself. Next, please. Yeah, I think we can briefly mention the general workflow. We have training controller, virtual training environment controller. We can basically trigger the training with this component. So it will trigger the metric refresh to SQL to JSON wrapper component. This one is this one will get the data from our scenario DB. As I mentioned, you can bring your own data and inject to this Postgres. And then our wrapper, JSON wrapper, will push this data to digital twin to give the overview of the system of your data. And schedule controller will filter will filter the data based on your criteria, and then finally it will send this data to integrated AI scheduler for the training. After all of these processes, when the training is done, we can return these results to virtual training control again, and then you can see the results. Next slide, please. So the second component is digital twin. Of course, this is a very simplified diagram of digital twin. We have 3 main components in the entire digital twin. So the first one is machine learning models that are capable of doing energy prediction and also carbon intensity analysis. Digital twin core is the component holding all of these system data, including failures and utilizations, for example, CPU, memory, or GPU utilizations. An API server is serving this system data to the clients. The biggest client of digital twin is, of course, AI scheduler. And also, we are storing this historical data in InfluxDB, and then we can revisit data and pull the data, and we can use it for future insights. Next slide, please. So the advantages of digital twin, of course, it provides real-time monitoring. For example, tracks node, job, and network status continuously. All of this data is coming from different resources and mainly from Prometheus. And it provides anomaly detection and energy prediction with machine learning models. And also, it's built on the top of MLOps components, for example, Kubeflow. So we can easily train these machine learning models with different type of data. And lastly, it provides carbon intensity models to predict this type of things and also to support environmental impact. Next slide, please. Yeah, let's continue with the integrated AI scheduler, probably one of the most important things in our DECICE framework. It provides AI-driven scheduling decision for Kubernetes-based HPC and cloud environments, and of course, edge devices. And it learns real-time from historical data using RNN and TCN neural networks. And it also provides fuzzy access controller to manage resource access across nodes. And lastly, it has interfaces with digital twin. So it can pull data, historical data from digital twin to train itself and also do some prediction based on this data. Next, please. Yeah, advantages of AI scheduler in DECICE framework. Of course, the probably the biggest advantage is it makes decisions based on the historical data, and this data is pretty comprehensive. So we have job nodes mapping in digital twin, and also we are collecting energy data. So it provides, it minimizes power consumption through energy-aware job scheduling, which is very important right now. And it dynamically adjusts job assignments in real time for efficiency and throughput. For example, if job fails, it will try to seek different options to schedule this job again on available resources. And also, we are storing this job node mappings and job results. So AI scheduler can learn from the past outcomes to improve the future decisions and prevent resource conflicts. Next slide, please. Yeah, the last one is SLARM integration. So Felix already mentioned about this as a challenge in the DECICE framework. So we are basically using SLARM REST APIs to integrate HPC side, because in DECICE project, we are trying to bridge the gap between Kubernetes and HPC side. So it's a pretty hard job. And we have advantage, for example, SLARM REST APIs. Luckily, they are providing sophisticated API descriptions so that once we integrate this one, our platform is acting like a single unified API endpoint for communication in hybrid systems, including cloud, HPC, and edge devices. And with this integration, we are able to offer fine-grained accounting for user group core hours, user and group core hour usage. And this one allows us to prevent exploiting our systems. For example, user can try to submit jobs even if they don't have enough core hours in HPC systems. So we can easily check that. Yeah, next slide, please. So the advantages of our SLARM integration is we are using the native SLARM API instead of, for example, shared service account, because we tried a couple of solutions, open source solutions to solve this problem, HPC problem in our project. But majority of those solutions are using one service account, which results in shared directories and shared resources. For example, if I want to submit a job with my own username, I can't do that with these solutions, and everybody will see someone else's data, which is not good, especially if we want to be GDPR compliant. And yeah, as I mentioned, it enables secure job submission, so everybody can submit their own job instead of using shared account. And we are trying to provide this ability with JWT token and also Unix socket. And there are some solutions also using integrating SLARM APIs, but they are using JWT token with unlimited lifespan, so people can easily exploit that if you don't have enough security in your system. So I think this is advantages of our implementation in DECICE framework. Next slide, please. Yeah, I think that's all from my side. Thank you.
Thank you very much for the really nice presentation and the nice overview provided, Miraj. So let's move to the next presentation, which will allow us to dive into our first project use case, and the presentation will be done by our dear colleagues from the Marmara University in Big Tree. Berkay, your phone.
Hello. Thank you. My name is Berkay Yaman, and I'm representing Big Tree in this project. And my presentation is about use case 1, which is related to intelligent transportation systems. And this use case is led by Marmara University, actually, and Big Tree is a contributor in that use case. So can you jump into the next slide, please? Okay, I will start with a basic use case description. The use case is actually, as I said, an intelligent transportation systems, or shortly ITS application. It's based on ITS application, and it's empowered by V2X communications. By V2X communication, we mean vehicle to everything communication. So in the use case, there is basically 3 components, which are, the first is the camera, which is stationary and mounted on a roadside in an intersection. And we have an edge device, or basically a node located in the edge cloud computing continuum, which is responsible for processing the frames captured by the cameras and sending the outputs to the roadside unit, which we call, we mean roadside unit is the third component of this use case, which is basically the infrastructure units for V2X communications, which enables vehicles to receive messages using V2X communication from the infrastructure. So basically, the camera captures video frames from the intersection, sends these video frames to the edge device or any node in the edge cloud computing continuum, and the edge device or the nodes sends these outputs to the RSU to be broadcasted to the nearby passing vehicles, so that the vulnerable road users can be detected using the video frames and can be informed to the vehicles, so that we can avoid possible collisions that might include vulnerable road users. And by vulnerable road users, we mean the pedestrians, handicapped users, motorcyclists, or cyclists, which are most vulnerable to hazardous or injuring collisions. So this use case aims to protect these users. By introducing DECICE, our main objective is to showcase that the DECICE framework improves the service availability and reliability so that the services can operate in adverse conditions. We also aim to maintain time criticality of these services. So these services need to be operate in real time. Any delays can cause life-threatening collisions, so that we should ensure the real-time operation of these systems. And also another objective is, as these services should be or will be deployed on ITS systems on a large scale, in a city scale, let's say, we are aiming to reduce the energy consumption by these services so that they can operate in energy efficient manner in a large scale. Can you jump into the next slide, please? Okay. Of course, as all other ITS services or applications, these use cases also have some constraints based on ETSI and 3GPP standards. We found 3 different constraints on this use case so that the system can operate safely. The first constraint is related to overall delay, which is the camera frames, the captured camera frames or the captured data from the intersection shouldn't be older than 300 milliseconds. So we should process these frames and send the outputs to the nearby vehicles in 300 milliseconds so that the data is up to date. Also, this is the second constraint comes from the 3GPP standards. So the transferring the data from the node, which is running the inference to process the camera frames to detect the vulnerable road users in these frames, should send this to the roadside unit in which the inference is assigned to. This delay should be less than 100 milliseconds. And finally, the final constraint is our inference, which is the object detection model, should be able to process at least 10 frames per second. This comes from another ETSI standard. So based on the standards, we have 3 constraints. In a DECICE perspective, we should enable these processes can be deployed in the cluster for fulfilling these constraints. Our approach is our setup is a multi-intersection setup. We have 3 different intersections which are located in West A, we call in Long. It's Vinet Lab site of testing autonomous vehicles, which is located in Marmara University campus in Istanbul. And by multi-intersection setup, we want to showcase the use of shared edge computing resources among the intersections. So there are different edge computing resources on the premises of different intersections. We aim to, or we want to achieve using these resources interchangeably so that we can provide energy efficiency by keeping some nodes idle and others are utilized on some level. And also we have a multi-cluster deployment. We integrated E4 and Marmara University clusters so that we can show the data locality or use of cloud resources in different geographical locations. By this setup, we are actually, I'm saying aiming, but we are actually currently done, I can say. We are aiming to effectively schedule of these workloads among the cloud and edge resources, and showcase the horizontal scaling to stay within the constraints. We are staying within the constraints, and also we are optimizing the energy consumption through bin packing so that we can ensure the reliability and availability of the system always. And also to achieve this, we are monitoring the network metrics in real time between nodes and the IoT devices, which are basically the roadside unit and the camera. And by this, we can always observe whether the constraints are achieved or not. Can you go to next slide, please? Yes, within this setup, our achievements are actually quite promising. We are now able to schedule these workloads among the edge and cloud resources, and also on the premises of different intersections by leveraging the digital twin, which is already mentioned, and the real-time network and node metric monitoring, so that we can ensure the safety by operating below the critical levels, which are defined by the standards. So we can serve up-to-date data to the nearby vehicles by placing workloads in relevant nodes. Actually, this is quite a promising solution, because in other systems other than DECICE, it's difficult to achieve constraints always while the network conditions or other conditions are changing. It needs some customizations in the system. So DECICE is actually helping this to achieve a dynamic constraints adapted system. Also, we leverage bin packing to reduce the energy consumption, as I said. As I said, we have an adaptive system which adapts to adverse conditions. We can keep the latency under safe limits, even under adverse conditions, such as a network delay can increase instantaneously. So in this case, we can reschedule the workloads based on the network metrics and device metrics. Also, we can use cloud resources based on the model accuracy. So we used Sedna for this. So the joint inference can be done when the edge computing resource cannot provide enough accuracy. Also, we can horizontally scale when the inference cannot provide enough frame production rates, so that we can scale the workloads. Then we can achieve the intended frame processing rate. And the most important part from my perspective is that we can reduce the energy consumption by 5 to 10% at least, which is very important in terms of large-scale deployment of these ITS use cases. Also, it's also a landscape where multiple ITS services operate in the same cluster. We achieve this by smart utilization of performant nodes versus energy efficient nodes when the constraints are fulfilled. And also, as I said, this is very important achievements to provide near 100% availability and always fulfilling the real-time constraints in a time-critical landscape. And thank you. This is my presentation of use case 1, and thank you for listening.
Thank you very much, Berkay, for the really nice overview provided. So let's move to the second use case, which is about the MRI scans. This use case will be presented by the University of Göttingen.
Yeah, let me present the use case 2. In this use case, we are trying to process MRI scans under some certain conditions. For example, we are trying to eliminate unregistered device, and also we would like to provide results under 10 minutes. Yeah, next slide, please. Yeah, I would like to briefly explain the definition of our use case in this presentation. So, as you know, MRI machines are scanning all of the body parts and also the brain, the different part of the brain. So they are generally processing this data inside the hospital, and this takes time. Generally, more than half an hour, maybe hour, and for the results you have to wait maybe at least 2 days or 3 days. And if you have an urgent problem, I think it's not that acceptable. So we are trying to get this data from the machines with edge devices. We want to do the analysis on cloud with the AI-powered solutions, and then we would like to return these results back to the doctor under 10 minutes. So as I mentioned, we are trying to prevent data storage on unregistered device, and also we would like to deliver these results under 10 minutes. Yeah, next slide, please. So for the analysis, we are using FastSurfer, which is based on AI models. I think based on convolutional neural networks, and we have 2 types of analysis. First one is segmentation pipeline, and the other one is surface reconstruction. Segmentation pipeline is for accurate segmentation and volumetric calculation of the whole brain and selected substructure, and surface reconstruction pipeline for cortical surface and mapping cortical labels. And segmentation analysis can be completed under desired time limit in our system, and we are also told that from doctors. In majority of those cases, MRI scans, we generally need segmentation analysis. And the other one generally takes about an hour. And these method is still using conventional methods. Next slide, please. Yeah, I would like to talk about our results on our Kubernetes clusters. So if we run segmentation and surface reconstruction with GPU and CPU combined, as I mentioned, it generally takes about an hour. So it doesn't matter if you throw more GPUs or CPUs. There are some limits that you can't reduce, maybe because of the nature of the problem. And if we only use segmentation analysis, we are able to complete it under 10 minutes without the help of GPU. But of course, if you add GPU, it generally takes a minute or so. So you can see all of these results here. And generally, if you combine segmentation and surface reconstruction, the fastest analysis you can get is half an hour. we are not able to reduce that required time for these analyses combined. Yeah, next slide, please. So for our future work, we would like to do the tests with the integrated AI scheduler. I mean, we are already doing it, but the results are not ready. That's why we didn't want to present them here. But our integrated AI scheduler is basically able to provide these decisions at millisecond level. So the time difference, we assume there won't be any time difference, but if it will be coming from the node level, not from the scheduler level. And also, we would like to integrate the solution. We would like to test the entire pipeline with the real systems. Right now, we are submitting from our users and also a couple of edge devices, but we also have to test that with the hospital itself. And right now, we must be GDPR compliant because MRI data is very sensitive data, so there shouldn't be any leak or any unregistered device or user. So on our side, it will take a little bit time, but we are on a good track. Yeah, I think that's all from my side. Thank you for listening.
Thank you, Miraj. And let's go to the very last presentation, which will be on use case 3. The presentation will be done by our colleagues from the University of Bologna, and then we can jump into the Q&A session. So please, guys, take over.
Hi, good morning, everyone. Can you hear me?
Yes. Yes, we
Perfect.
can hear you.
Yeah. So I'm Sebastiano Mengozzi from University of Bologna, and I would like to present to you the use case 3 that we developed for the DECICE project. Next slide, please. Thank you. So our use case wants to leverage robotic systems and autonomous systems to gather in-field data for intelligence support during some emergency scenarios. And we plan to use a priori knowledge provided by satellite images that are available for disaster situations. And we use this for creating a plan of exploration of interesting areas for the emergency responders. And once we create an exploration plan with autonomous systems, our objective is to gather data directly from the field by exploring the interesting areas and with the usage of autonomous quadrotors. And moreover, we want to process this data on board and gather information that could be meaningful for emergency responders, such as, the presence of people in the field or some destroyed areas that we want to explore in more detail. So the objective of our use case is to demonstrate that DECICE can improve the emergency response system, and while keeping the task latency of our application compatible with the real-time execution that we need to gather field data and to create fast plans of explorations, and while enabling let's say features that are not available for classical methods adopted in these cases, like saving energy on the edge platforms, because we want that our quadrotors are able to explore for the most time as possible, and they are battery powered, so we want to save energy on those platforms and be robust, for example, to the loss of one in-field devices, and able to increase the robustness of the overall system. Next slide, please. So this is the let's say technological architecture that we developed to deploy our use case on the computing continuum and on our target architecture that we have for the project. And commonly these kind of tasks is not executed in a cluster, but maybe with the tasks that are running on fixed devices, such as the computing the computer that is on board drones or some base station. Instead, here we based our development on the ROS2 framework that is commonly used in robotics, and we encapsulated our ROS2 nodes inside Kubernetes pods. And this enables the scheduler to move pods around the computing continuum and schedule on different hardware platforms, hardware nodes. And here we can see also the data processing and data flow of our application. So we have the streaming of satellite images to subsequent images before the disaster and after the disaster, for example, a wildfire. And we compare the two images to identify where the wildfire happened. And then we send this information to another processing node that creates a plan of exploration of the wildfire area. Once we have the plan, we have some waypoints for our autonomous drones that are deployed in the field, and then these drones can follow the goal and process the data. For example, they can acquire images with more detail in the field and process it through, let's say, we use it as a workload YOLO network, so also running AI tasks. And to do this, we also needed to make all the nodes communicate with each other, and for this we use VPN and Cilium to enable the discovery of the nodes in the network. Next slide, please. So we successfully deployed our use case in the cluster that is the target hardware for the DECICE project, and we measured some of the KPIs that, as I told you before, we need to be compliant with in order to having the real-time availability of our solution. And in particular, we measured the delay of processing the satellite images to create a plan, and also how much time do we need to process an image coming from the field using YOLO networks. And moreover, we also tested the case in which we lose one field device, and we were able to reschedule actually the job that was running on the simulated lost device onto another device that was replacing this one. And moreover, we are working through last measurements to compare our solution and to gather all the data, and also integrating the AI scheduler in order to improve the KPIs that we have, and also enable in particular the energy KPI on the edge device. And that's all from my side.
Great, thank you very much, Sebastian, for the really nice presentation. And now we come to the interesting part of our webinar, namely the discussion round. So the participants in our audience are welcome to ask questions to our presenters. If there are no currently questions, I would like to just ask you questions concerning each use case. Regarding the use case one, I would like to ask the responsible leads, what are the specific challenges that you foresee in integrating and deploying the Cloud Edge platform for intelligent intersection applications, and how does the DECICE platform addresses these challenges? Just to highlight this aspect.
Yeah, the main challenge is the landscape is highly dynamic, I can say. So that the system should be adapted to varying conditions, such as the network changing network conditions, or increasing stress on some devices, or against tampering. DECICE can effectively address these solutions by continuously monitoring all of these conditions via a digital twin, and rescheduling or horizontally scaling, or doing joint inference on these workloads, so that the system can stay. The most important thing is availability, because we need to provide real-time services, so that we can improve the availability using these dynamic arrangement of the workloads.
Great, thank you. Any questions from the audience regarding the use case 1? If they're not such, I would like to ask a few questions regarding the use case 2. Regarding the GDPR compliance, how does the DECICE framework ensure GDPR compliance in patient data privacy for the MRI transfers?
Yeah, we have pretty good authentication mechanism. So either the target person or device, it doesn't matter. They should be registered to our systems to send the data or to submit jobs. So we are providing GDPR compliancy with this type of things. And also we are storing the data. We are trying to store the data on our own registered systems, and when we want to do the calculations, it's not going to be on customer side, so it will be on our systems. So that, I think that's a good approach to provide the GDPR compliancy.
Great. And one more last questions for use case 2. How are restrictions on unregistered devices enforced in your case?
Sorry, my internet connection is
No
not good.
problem. I can repeat the question.
Yeah, please.
How are restrictions on unregistered devices enforced in your case?
For example, we basically request everything to user or devices to be registered first with the main access points. So, for example, when the registered device wants to send data or wants to submit a job, it will be blocked immediately, because we are getting the information first from the device, and we are comparing this information in our own system, in our own database. If we don't find any match, so basically it will be blocked immediately.
Great. Thank you very much for the answer. Guys, if you don't have any questions regarding use case 2, I would like to address now use case 3 with 2 questions regarding the real-time coordination across drones. How will the platform manage this? So how will the platform manage real-time coordination across drones, edge devices, and cloud infrastructure during emergency missions. Maybe you mentioned it during the presentation, but I believe it will be interesting to highlight it one more time.
Yep. Actually, the coordination of the drone in the field is the result of the processing of the satellite images to create an exploration plan. And the DECICE framework can enhance this by actually scheduling the processing of images and then the plan creation into let's say the most suitable hardware nodes, and having the fastest response for that is compliant with real-time mission execution.
Great. And one more last question for me. How does the platform ensure secure data handling in such cases?
Yeah, actually, we used a VPN connection to exchange data between nodes, and so we actually use this as a, let's say, secure data connection in this case.
Great. Thank you very much, Sebastiano, for your answer.
Thank you.
Are there any questions from the audience? If they're not such, I would like to move toward the ends of our today's webinar and to invite all participants to register to our newsletter in order to keep up to date with any further developments coming from the DECICE consortium and DECICE project. Also, to exploit any networking opportunities, please feel free to visit our project website or get in touch with us via our Twitter and LinkedIn project channels. So on the behalf of our coordinator, the University of Göttingen and the DECICE consortium, I would like to thank you for joining us today and wish you a nice rest of the day. Thank you, guys.